All right, today we're going to look at the difference between explicit and implicit differentiation. Everything that we've been doing so far is explicit. In other words, one of the variables has been explicitly given to me in terms of another one, like y equals 3x plus 1. I know what y is basically in terms of x. Okay? Or s equals 5t minus 3. I know what s is with respect to t, and then the last one there you can see that I know what they are. What's going to happen is sometimes we're going to get equations that are, unfortunately, implicit. Okay? For example, x times y equals 3 is an implicit form because no one of the two variables is necessarily solved for. Now, in this very first one, x times y equals 3, is it possible to get one of the variables by itself? It is, and so could we do that one explicitly if we wanted to? Yeah, we could just have to rewrite it. The second one, x squared minus 2y to the third plus 4y equals 2, well, to get y all by itself would be rather complicated in that one. Okay, because we have y to the third and y. Okay, and so that's where we're going to want implicit differentiation to help us out. And you can see in this last one, y to the third plus y squared minus 5y minus x squared equals negative 4. We're going to want to be able to take that derivative another way. Because a lot of the derivatives that we're doing are with respect to x, which means we would like y to be all by itself. Believe it or not, you have been doing a little bit of implicit so far. It's just I don't really talk about it that way because it could very well be confusing. Okay, I think I've come up with a way for students to kind of understand this one. So let's just try a few here, and we'll see kind of if this makes sense. So it says differentiate with respect to x. Now, well, there is x. That's the variable, right? Okay, so this isn't that bad. This is just which rule, which shortcut? Power. Now, technically, I should have been having you do this, but I haven't been. So we got the 6x, right? And really, I took the derivative of x with respect to x, correct? Have I had you write that down at all? No, I haven't had you do that yet, have I? Why wouldn't I do that? Because what is dx over dx? It's something over itself. So this right here is really just 1, right? So you see why I maybe haven't had you write that down? It's kind of a waste. Because we know the answer is 6x, correct, in this case? We know that one. All right. So this one over here, if it's with respect to x, though, well, it's very similar to a. But what we're going to do is we're going to do 3 times 2. There's your 6. Y to the second. But I took the derivative of y with respect to x. Have we seen that notation somewhere before? Yeah, we have. What is that notation? dy dx really just means derivative, right? So have you really kind of been doing this? You really haven't. I'll show you why in a spot in a second. Or actually, I could probably do it on this one. If I did have y equals 3x squared, haven't you been doing this side implicitly the whole time? Because what is, if you do it, it's really just, well, what's the derivative of y? It'd be 1 derivative of y with respect to x, right? But we've just been writing y prime on that side. But isn't y prime and dy dx the same thing? So you really have been doing implicit this whole time. I just haven't talked about it that way. Okay, so how about this one down here? So it's the derivative of this stuff with respect to x. How about this first one? It's an x. So it's 1. And I'm going to keep writing this until you get it. Derivative of x with respect to x, right? Because that's actually what I took the derivative of in here, right? Plus 3y, so 3. Just using the power rule, right? But I took the derivative of y with respect to x. Of these two, which of them can I simplify? The dx over dx is just 1. So really this is just 1 plus 3 dy dx. And I've never really seen it quite done this way. What's that? Because I don't know what dy dx is. I know that dx over dx is 1, though. I know that. That's guaranteed. Okay. Perhaps you'll see it the further we go. Okay. Because eventually our job is going to be to get that by itself so that I have just the derivative. Eventually. Okay. But I don't really have any equal signs in this one, right? So that maybe is why you're confused. The reason I didn't want to put equal signs is because I didn't want to sit here and worry about this the whole time. Okay. I thought ahead. You know. What unfortunately has to happen on this one? There's multiplication, so I have to do product rule. So I would say x is the first one and y squared is the second one. Excuse me. So let's scroll down because I think I'm going to need some room here. So again, just hang with me for now. You'll get used to it. So write down the first one, right, times the derivative of the second one, which is 2y, but then I took the derivative of y with respect to x, right? Done? No, what? What do I gotta do? Oh, we gotta do the other half of product rule. Okay, plus. So write down the second one. So do I write dy dx? Did I take the derivative of y with respect to x in this spot right here? No, I just wrote down y squared, right? So now we have to take the derivative of x, which is 1. And then really, I took the derivative of x with respect to x. Okay, pretty soon a lot of you are going to stop writing that, and that's fine. But the reason I'm writing it now is so that you really know why we're writing that one in, because otherwise it doesn't seem that important. Okay. So to clean this up, we really have a 2xy dy dx plus y squared, right? Everything else over here is just times 1 times 1. Okay. How are we doing on that so far? You doing okay? Because this is normally not a very easy section to get. Hopefully this way of teaching it will help. All right, let's calculate the derivative with respect to x for xy equals 3. I'm actually going to do this. In the past, I've done this 2 ways. Hopefully you'll be willing to let me do that again. It's up to you. Doesn't matter? Because isn't this the one earlier that we said we could really make this explicit, couldn't we? Why don't we do it that way first? Let's make it explicit. And what do I mean by that again? One of the variables is solve. So what are we probably going to solve for? Probably get y by itself, right? So to do that, y is really going to equal, we're just doing algebra right now. We're not doing derivative, right? 3 over x, are we in agreement? Yeah. Or in other words, if we're going to do it, we'd probably write it as that, right? 3x to the negative 1. I mean, for the derivative, right? Because now we don't have to use quotient rule now, right? Now we can just use power rule. Do you see how you could use quotient rule on 3 over x, though? It would work, right? Yeah, quotation rule, yeah. So negative 3x to the negative 2. Are we in agreement? I hope so. So it's negative 3 over. Did I forget anything? Like, is there a chain rule in here that I'm forgetting, or am I doing good? Ah, very good. Y prime. Because really, isn't that the implicit part of this, right? But again, it's not. You don't have to look at it that way if you don't want to. At least not yet. But if we begin to look at that, that's kind of where dy dx is in this problem, right? It's on that left-hand side. It did come into play. So did I miss anything there? Is that pretty good? Yeah. Question? Okay, the question is if we're doing explicit, could we do x equals 3 over y? You could, but we'd have to change. That would still kind of be more implicit because we do want to do with respect to x. All right, and so we'd be doing the derivative of y with respect to x, and so we have to add that in. Okay, because a lot of times we are trying to remember our derivative. We want to call on an x value to compare the derivative to the original, keeping that x value the same in between both. And that's really what we're looking for. Yeah.
Technically, when dx over dx be on the right side, right, just get this, because you're finding.
Right. So technically, if I wanted to, what was just said is I could put that dx over dx in here, but I didn't this time because we didn't do the dy dx on this one. But yeah, and then it just becomes the 1. So it's still technically kind of here. It's just a lot of times when we did it before, we didn't write it, which is why I didn't want to confuse you by writing it this time. Okay? All right. Then over here, let's just do it another way. Let's do it implicit. So this, unfortunately, is going to be product rule, right? So here we go. Hopefully this will help you see that it really is, could possibly still be getting derivatives. So first one times the derivative of the second one. Well, what's the derivative of y? It's 1, but it's the derivative of y with respect to x, right? Plus second one. Now this time I'll probably write it, seeing we're kind of doing it more implicit, okay? So now I gotta take the derivative of x, which is 1, dx equals, so now there is an equal sign, right? So if you take the derivative of the left side, you better take the derivative of the right side. The derivative of the right side is very nicely 0, because the derivative of 3 is just 0, right? So dx is just 1. So really that term right here is just y, right? This term here is x dy dx, right? When we have derivatives, what do we normally have by itself? We have that slope portion by itself. Of what I have written here in red, what part of it is actually the slope part? the the dy dx, right? Over here we have it by itself. Well, let's get it by itself over here. So what are we going to do? Subtract y. And divide by x. So apparently, I'm running out of room here. Apparently, dy dx equals negative y over x. Boy, I'm kind of a liar, huh? I told you it was going to be the same thing. Those don't look the same to me. Over there I got negative 3 over x squared. Over here I got negative y over x. What's going on? How's that work? What's that? Yeah, they are, because this is y prime over here on the left that I have circled in red. That's dy dx. It's the same thing. It's just a different notation for it. So aren't these supposed to be the same thing? Man, I'm just a big liar, I guess. Any ideas? Really? No? Yeah, got something? Because I didn't do either one of these wrong. Okay, we notice the numerators are both negative, so that's a good thing. The denominators both have an x, so we're off to something. But the one over there in green doesn't have a y, does it? Yeah, replace y with something we know it to be for true in this problem, and we know for a fact that y is 3 over x in this problem, right? So really, if I wrote it this way, I could write it as negative 1 over x times y over 1. Do you agree with that? I could write it that way, right? This one over here. But what is y? Somebody just told me that y in this problem has to be, which if I multiply it out is so are they both the derivative? Yes. Why is this one over here on the left maybe more handy when it's, what's it only asking for? It's only asking for x. What did I tell you was going to happen this year? We might have derivatives that ask for both x and y. So will both of these actually give me the slope at any particular point I ask it? They will. Will they give me the same slope if I give it the same point? It will. Okay, it's just one form is maybe more friendly than the other. Okay, and that's for you to decide which way. So they do work. All right, and the whole idea is to get dy dx by itself. So let's try it here. Calculate the derivative with respect to x for that, which I believe is another one we saw earlier. Evaluate the derivative at 2, 0. Is this one that we can do explicitly? Unfortunately, no. Because what would you have to do? You'd have to get y by itself. And there's 3 different ones at different exponents. That's not going to work out so well. All right. So let's do it implicitly. Here we go. Let's do the first term. Y to the third. The derivative is, with respect to x, of course, 3y squared dy dx, right? Plus, so this is y squared, so I have to do product rule on y squared. You could, right? But that'd be waste your time, right? So it's 2y. You notice what I do with my dy dx's, though? Kind of make them so I can locate them, kind of put them in parentheses. That's just a personal thing. Minus 5y, the derivative of that is minus 5. And minus 2x. So at what point do you want me to stop doing the dx thing? Right now? You're good with that? Okay? Because really, you could put it there, right? And that equals, you got to take the derivative of that. Don't always think it's 0. All right? Some people think that, and make sure there's not something else there. Like if that was a negative 4x right there, obviously I would have to be careful. It's not just 0 all the time. Yes? Anytime that you take the derivative of y with respect to x. Yep, anytime. And again, I could put dx anytime I take the derivative of x with respect to x, but after a while we kind of get sick of that because we know it's just 1 anyway, so we get tired of it, right? Because I could really write dx right here, right? Okay, but we just get sick of it. Whoa, that's way more terms than we had in the last one. Any suggestions here? Because what do we really want to know? I want to know what is dy dx. Well, we could quit, but yeah, we want it by itself though. And there's 3 of them. But wait, they all have the same exponent though, don't they? It's dy dx to the first. Hey, I can factor this out, I betcha. But that darn negative 2x does not have a dy dx on it. Move it, get it out of there. How do I get it out of there? Just erase it?
Yeah, quick.
No, you add 2x to the other side. So now, this is gone. I've got all of that on the left hand side in blue with dy dx's on it, equals 2x. Well, they all have a dy dx. Well, why don't we factor it out?
I don't want
So it's 3y squared plus 2y minus 5 equals positive 2x. Had to save that one there. I almost wrote negative 2x. It was close. Boy, I wonder what the derivative is. Yeah, it's kind of tricky. Oh, we could get dy dx by itself by dividing by all of that stuff in parentheses. Who said we can't do that? Because I just did. Because 3y squared plus 2y minus 5 over 3y squared plus 2y minus 5. That's 1. It's a weird form, but it is. There's your derivative. 2x over 3y squared plus 2y minus 5. All right, then. Yeah, we have to find the, well, it says calculate the derivative. We did that. And then evaluate the derivative at 2, 0. That means every place in that derivative I see an x, I put 2. Every place I see a y, I put 0. So this one actually does ask for both of them, right? This is probably one of, the first time it actually has happened. So what we got here, we got 2 times, what do we put in for x? 2. Right, we put 2 in for x. And then for y, we're going to put 0. Well, 0 is kind of a nice one because if I put 0 in there, that whole term is 0. Plus 0 minus 5. So the slope is negative 4/5, or however you want to write it. So of this graph, let's face it, this would be pretty hard to type into your TI-83. All right, we could type it into other software, or I'm not sure if the Inspire. I think you can type it in that way, can't you? I think you can type it straight in like that and it would graph it, but a lot of them you can't. So of a graph that we've never really seen, we now know the slope going through that point on that graph is negative 4/5. Slope of the tangent line, otherwise known as the instantaneous rate of change. Okay. Or potentially velocity, depending on if that's the position time graph. Okay. How are we doing? Implicit. All right. Actually, you're doing quite well compared to other years. All right. So determine the derivative with respect to x. For that, evaluate the derivative at square root of 2, 0. Wait. Well, we can't really get y by itself, can we? We could try. Yeah, let's not do that. No, we're not going to try. We're going to do the derivative implicitly because it's quicker. Here we go. 2x. dx. I'm going to write it this time because I can. Minus 6y squared dy dx plus 4. Equals, again, don't always assume it's 0 because I could easily move the 4y over to that side or something like that. So what we really got is we got 2x minus this stuff plus that stuff equaling 0, right? So what's our goal really was to get dy dx by itself, and we can because all the dy dx's that we have are to the same power, but we still got that 2x kind of in the way. So we'll move it. So subtract 2x. So I'm going to factor this out right now, if you don't mind. it just 4? Yep.
There should be an equal sign outside the parentheses.
We're almost there at this point. I think most of you are working on your own now. You're not even looking up here, which is okay. That shows me that you at least have some idea of where things are going. Yeah, either that or I'm going too fast. One of the two. And divide. How about simplified form of the derivative?
The negative.
Negatives do not cancel, not quite. I mean, we could take a negative out of the bottom. I wouldn't even deal with that. But we can take a 2 out of everything. So negative x over negative 3y squared plus 2. No, we wouldn't have to multiply everything by 2 because we kind of factored a 2 out of the top and we factored a 2 out of the bottom, and so we canceled that. Yep. Yep. We could factor a negative out of top and bottom if you wanted to, I mean, if that's what you really want. But realize if we factor the negative out of the top, it becomes that, and then it would be 3y squared minus 2. But then keep in mind that that's something that a textbook might do. You might have this answer sitting over here, and then they give you this, and you're like, oh man, what in the world? What happened? Well, you got to realize, oh, they just kind of took some negatives out, you know. So. All right.
And what they gave you for the order
Square root of 2, comma 0. Square root of 2 for x, right? Is that what it was? And what was the other one? I got to look at my sheet here. 0. Okay. So we got to put, so x is what? Square root of 2? Where are we at? So square root of 2 over negative 2. Oh, that looks like a familiar number. Negative square root of 2 over 2.
Unit circle.
Interesting. Yeah, that may have come up in the unit circle a time or two. Yes, we have a question. The main reason is with respect to x. I'll be honest, it's kind of that's how it was chosen to be done. We could have obviously flipped everything over in calculus, but the main reason is because that's our kind of our slope setup. Is x is on the bottom, and now if I go from the original to a derivative, I can keep that x value that I'm concerned about constant between the two, and then just find either the y value being the slope or the y value being the actual y value, or the y value being the, well, we haven't talked about it yet, but concavity and all sorts of things. Yep.
So as of now, we don't have to be concerned with respect to y popping up?
The question is, do we have to be concerned with respect to y? And not right now, no. It does happen later in the year that we do flip things with respect to y, but it is commonly done with respect to x. But that's going to be when we start finding volumes of very strange objects. Okay. Any other questions?